Hello, this is Math 2231 coming to you from the College of DuPage during the summer of 2020, and the title of this lecture is Properties of the Definite Integral. Last time we defined the definite integral as the limit as n goes to infinity of a sum related to the function, and this ended up being the way we sliced up the x-axis. You know all about these limits, so that's good, but we're going to review a little bit about the summations and things that you need to have in your mathematical toolkit. First thing is you need to understand what these finite sums are in the sigma notation. So the sigma notation enables us to write a sum with many terms in a compact form. So instead of writing a1 plus a2 plus a3 plus dot 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 plus a sub n minus 1 plus a sub n, we can just say this is the summation, that's the sigma sign, k equal 1 to n. I put k equal 1, then I put a plus sign, then I put k equal 2, put a plus sign, so on and so forth, and I do that all the way up to n. So the Greek letter sigma stands for sum, and the index of the sum, k, that's this letter here, tells us where the sum begins and where it ends. And you can use any letter to note the index, but I, J, K, and N are customary. And so here's the notation broken down with what all these terms mean. So a sub k is the formula for the kth term. That's the top index, that's the bottom index, and that's the sum. So for example, you could write the summation of the squares from 1 to 11 this way, compactly. And if you're talking about function f of I for integers 1 through 100, instead of writing 100 terms, you could write this. Although the starting index often is 1, it could be any integer. You also might recall things you learned in your pre-calculus about these summations. If you add a1 plus b1 plus a2 plus b2 plus a3 plus b3, addition is commutative, and so that's the same thing as adding all the a's together and then adding all the b's together. This is the same kind of thing, except we're talking about minus b's, and you're factoring out the minus sign. This is the distributive property. So if I have c times each term in a sum, I can pull the c outside of the sum, and that's true for any number c. And this one is one that students sometimes have problems with. If you add, you see there's no k here, so that means you're adding, when k equal 1, you're adding c. When k equal 2, you're adding c. When k equal 3, you're adding c. When k equal n, you're adding c. So how many times did you add c to itself? N times. We're going to be using these formulas, so make sure you're recalling these. And finally, there are three formulas that come up in a lot of the problems that you will do, and you want to maybe memorize these. So if I add up the first n positive integers, I get n times n plus 1 over 2. If I add up the sum of the squares of the first n positive integers, I get this, n times n plus 1 times 2n plus 1 all over 6. And if I add up the first n positive integers, the cubes of each one, I will get n times n plus 1 all by 2, whole thing squared. Okay, so now we're going to use some of that doing a calculation. So we're going to use the definition of the definite integral to compute the following. So we want to find the definite integral from 0 to 2 of x squared plus 1 dx. Okay, well, first thing we do is we slice up the interval. We take the length of the interval and we divide it by n. So each delta x is of length 2 over n. That means the intervals that we've sliced things up are 0 to 2 over n. This is another interval of 2 over n, 2 over n, so on and so forth. And so you can see that the right hand endpoint is 2I over n of the ith subinterval. So this is the sum we're going to take the limit on. So this is the summation of the function values at these points that we're picking, and we're picking the right endpoint, since it doesn't matter what endpoint we pick, times delta x. So we're going to then have the summation that just stays there. Delta x is always 2 over n, but now we're taking this 2I over n and we're plugging that into our formula, which is x squared plus 1. So when I plug that number in, I get 2I over n whole squared plus 1. So it looks like that. I square this, I get 4I squared over n squared. And then I distribute the 2 over n across this quantity. And so I get the summation I equal 1 to n, that is going to be 8I squared over n cubed plus 2 over n. Make sure you're following all these calculations. Ask questions as you do not understand them. Okay, so we continue. This is what we had on the previous page, but now we're doing it term by term using one of those properties in our toolkit. Now, here you're summing on I, but 8 over n cubed, neither one depends on I. So that means it's a constant as far as the sum is concerned. So I can jerk it through the constant. I jerk it through the summation because it's a constant. And here, 1 over n does not depend on I, so I can jerk that through the constant. So I have this. Now I have 8 over n cubed, and this is one of the formulas that I told you we wanted to know. And so there's going to be n times n plus 1 times 2n plus 1 over 6, plus this is 1 over n times 2n. So when I multiply these together, I just get 2. When I multiply these together, I get this in lowest terms. I canceled a 2 between the 6 and the 8, and I get this expression. And that simplifies to this. So now what I'm going to do is I'm going to take the limit as n goes to infinity. But think about this. The limit as n goes to infinity of, this is quadratic. It has an n squared as the highest power. This has 3n squared. This is a limit we learned back in the beginning of this course, and that is 14 over 3. So the exact area is 14 over 3, and in the previous lecture we computed approximately what this is, and you'll see that those are all very close to 14 over 3, but 14 over 3 is the exact answer. Now I'm going to ask you to compute using the definition, this one, the definite integral from 0 to 3 of this quadratic dx. And what you're finding is this area. You know what to do. Let's see how you did. Okay, so what's going to happen is each interval is going to be of length 3 over n. And I'm going to start, and in this case we're using the left hand endpoints. This is different than what I did on the first one. And so each of these values then ends up being 3 times I minus 1 over n. So that's where I get this value. That is what the left endpoint is going to be. And that is 3 over n. So this is the sum we have to evaluate. So the 3 over n just sits there, but I take this expression, 3 times I minus 1 whole, all over n, and I substitute that into my f of x, which is 3 plus 2x minus x squared. That's what I did in this step. And then I distribute this 3 over n across those three things, and I get this summation. And now I'm going to break this in using one of the properties. I'm going to break this into the summation of this, the summation of this, and the summation of this, and I get this expression. Now I'm going to pull the constants out. So here I am going to pull out 1 over n, and I will get 9n over n. Here I will pull out 18 over n squared, and here I'll pull out 27 over n cubed, and I have these summations. Now these start at 0 and go to n minus 1. if you look at what we're plugging in. And so our formulas actually would be calculated for 1, 2, n minus 1. So that's what we get when we change the variable to j, just to make it match up with our formulas. And so now we're going to be using our formulas. So I get 9. This is 18 over n squared. This is going to be n minus 1 times n over 2. Minus, this one is a summation of the squares. This is going to be n minus 1, n, and 2n minus 1 over 6. Make sure you understand how I adjusted the summation index. And so now I multiply things together and I get this, and I got this, and now I'm ready to take the limit. So the limit of the sum is the sum of the limits. So this one, it becomes 9. This one also becomes 9 because you have 9n over n as the leading terms. So it is 9, and this is going to be 9, but this is going to then be minus and it's going to be, let's see, this limit here is going to be 1, so that is minus 9. Okay, so 9 plus 9 minus 9 ends up being 9. And so that is our answer. We'll continue this in 31.